Welcome to our Math 154 videos. In this video we're going to find the absolute maximum and minimum values for this function, f of x equals sine of x plus cosine of x, on the interval 0 to pi over 3. So the first thing we want to do to find the maximum and minimum values is figure out where the critical points are. In order to find the critical points of the function, we're going to need to take its derivative. So f prime of x is going to be equal to cosine of x, that's the derivative of sine, and then the derivative of cosine is minus sine of x. Alright, where the function is critical is where this derivative is equal to 0. So that's going to mean cosine of x is equal to sine of x, if we add sine of x on the other side, or cosine of x over sine of x is equal to 1. Note cosine of x over sine of x is just tangent of x, and tangent of x equals 1 at x equals pi over 4. So this is our critical number. Now that's the only critical number, so we only have to worry about pi over 4 and the endpoints. So this is what's called the closed interval method. Since we have the function and it's continuous on this closed interval, we can just evaluate f at its endpoints and at the critical points. So I'm writing those down here. So the endpoints are 0 and pi over 3. And notice we're going to plug those back into our original equation, f. Alright, we're not plugging them back into the derivative. We want to find what the actual value of the function is at these points. So at f of 0, we're just going to get sine of 0 is 0, so cosine of 0 is 1. Then at f of pi over 4, we're going to get the square root of 2 over 2 plus the square root of 2 over 2, and that's going to be just the square root of 2, which is approximately 1.41 if you were to plug that into a calculator and get a decimal. Then f of pi over 3, sine of pi over 3 is the square root of 3 over 2, and cosine of pi over 3 is going to be 1/2. So if we get a decimal approximation for that, that's 1.37. So what's the highest value? 1.41. So this is our absolute max. And the lowest value of those three is 1. So this is our absolute min. So f of 0, so at x equals 0, we have a minimum value of 1, and at x equals pi over 4, f of pi over 4, which is equal to 1.41, is our absolute max. So here's our second example. We have f of x is equal to x e to the negative x, and we have that on the closed interval 0, 2. So we're going to use the same method as the last problem. First we're going to take the derivative. So f prime of x is equal to, now notice we have to do the product rule here because we have x multiplied by e to the negative x. So the derivative of x is 1, then we have e to the negative x, plus the derivative of e to the negative x, which is minus e to the negative x, and then we have to multiply that by x. Alright, so we can factor out an e to the negative x, and then we have a 1 minus x. So we want to find where this is equal to 0, because where the derivative is equal to 0 gives us our critical values. So notice e to the negative x is always positive. So that's not going to give us a critical point. So the only other option for a critical point is when this term is 0. So that's going to mean we have a critical point at x is equal to 1. Alright, so there's one critical value, and we just need to check the original function value at our endpoints and at our critical value. So notice we're taking the original function. I see a lot of students trying to plug these critical points back into the derivative. We already know the critical value has a derivative of 0, but that's only to figure out where there could be a potential maximum or minimum. Okay? So we need to plug these values back into the original function. So f of 0 is obviously going to be 0 because we have x times e to the negative x, and when x is 0, that's 0. Then f of 1 is going to be 1 times e to the negative 1, or 1 over e. And if we get a numerical value for that, it's approximately 0.37. Then f of 2 is going to be 2e to the negative 2, which if we plug in a numerical value for that, we're going to get approximately 0.27. So these are all the possible places for an absolute maximum or minimum. So turns out the lowest of these three is going to be f of 0, which is 0. So at x equals 0, we have the function attaining a minimum value of 0. So this is our absolute min. Then the maximum value of all of those is 0.37. So that's our absolute maximum, and the function attains the absolute maximum value of 0.37 when x is equal to 1. Now you might wonder what's the difference between this and using the first and second derivative tests. So the closed interval method is obviously for a function on a closed interval, like what we have here, and we use this to find the absolute maximum or minimum. Now when we use the first or second derivative test, those help us find local maximums or minimums of a function over the entire real line. Now sometimes they could help us find a local maximum or minimum value in an interval, but when we have a closed interval, like in this case here, it's just easier to use the closed interval method and check both of the endpoints and any critical numbers.